Conventional refrigerators consume about 20% of the total electrical energy of the world. But the efficiency of these refrigerators is not very high, only about 60%. So our goal is to make a refrigerator that could have higher efficiency and also avoid another major problem of conventional refrigerators. They use gases that powerfully contribute to global warming.
So how do the team plan to overcome the problems of environmentally unfriendly refrigerant gases and the low level of energy efficiency which arises from the effort it takes to separate the cold air inside the fridge from the warmer air outside?
It's been known since about 1805 that if you take a rubber band and stretch it, it heats up. On the other hand, when you release stretch, it cools down. We get cooling from a rubber band by inserting twist in it, which heats it up, and then removing twist, which cools it down.
So winding and unwinding elastic, and maybe other fibers too, has a similar effect to stretching and unstretching it. It can change its temperature.
We can take ordinary fishing line and insert so much twist into this fishing line that it coils. If you stretch this fishing line, you get heating, and if you release this stretch, you get cooling.
This happens because when a coiled object, like a spring, is being stretched, it actually twists, and this led the team to wonder what would happen if they first twisted their fishing line in one direction and then used the twisted fiber to fashion a coil that itself spiraled in the opposite direction.
The cooling process is caused by a change in fiber twist, because if you stretched a metal spring, the spring elongates not because the wire in the spring is getting longer, it elongates because the wire is twisting. Now, if we use a different handedness of the twist within the polymer fiber compared to the twist that makes the coiling, we can make a remarkable material, a material that is unlike any other materials in that when you stretch it, instead of heating, it cools by as much as 20 degrees. We can cool flowing liquids, and these liquids can be fed into coils to provide the cooling needed for a refrigerator.
And done this way, the efficiency of the process is at least 67%, which is already a big improvement over conventional fridge technology. But how would this work in practice? While the size of a fridge that relies on stretching fibers would be somewhat impractical, a fridge that uses twist would only need a motor that twists and untwists one or more fibers immersed in water, and then this cooled down water could circulate, for example, through pipes in the fridge walls, cooling the interior down.
I hope to have a twisty fridge at my home very soon, but it won't be a commercial product for at least 5 years. This is the first work, the first discovery that twist can be used for refrigeration. And nothing has been done as far as optimizing materials or devices. This is exciting things that can be done in the future and will be done in our laboratory, and I'm sure numerous laboratories around the world.